Good morning and good evening, everyone. This is Robert Zych. Um, Today is November 4th, 2025. Welcome and to our speakers, Tarun and Jiapeng, and everyone in attendance today. Thank you for presenting, joining, asking questions. Um, this is the fifth meetup in this series of Pinot contributor calls, the last one for the year. If you have any topics for next year, Shang, my typical co-host, isn't able to join us today, but we are planning some events for next year. So we welcome your ideas and topics, and always interested to hear all of the great contributions to the Apache Pinot project that you all are making. The first topic that we have today is from Tarun on a topic regarding compaction, which is near and dear to my heart as being an original contributor to Upsert compaction and a fan of Upsert. And so please take it away, Tarun. Oh,
Thanks, Robert. Let me just share my screen. Okay, cool. Yeah. Hi, everyone. My name is Tarun. I'm from Uber, and I've been working with a lot of upsert use cases at Uber. And to support the scale that we have at Uber, we needed to make few optimization or the improvements to the existing upsert features, upsert that Pinot supports. So in this talk, we'll specifically talk about two features that we have contributed from Uber side, that is segment merge compact and the commit time compaction. So let's start with the talk. We'll go into uh, so the agenda of this talk will be we'll start with the upsert background, and we'll see what's the evolution of upsert table optimization at Uber, and then we'll dive into the two specific topic that we want to discuss today. Yeah. So let's get started. So first of all, what is upsert? So upsert is nothing but update plus insert, which means if the record already exists, we update that record, and if there is no record found for a primary key, that means it's a first occurrence, and we insert that as a regular record. Now, Pinot is at the end, it's a OLAP store, and it's an up and only architecture. It follows an up and only architecture, which means we cannot do a point update where you can point to a particular key and then directly update the record. You always need to insert it, which means to support upsert in Pinot, we came up with a very a mechanism where we keep on inserting the data at the end of the consuming segment, but then we maintain an upsert metadata map that points to the latest location of a particular primary key, which means if there is a if there is an update coming in for an existing primary key, we always insert a new record, which means if there are multiple updates, we might end up with a lot of records for the same primary key, of which only one of them will be valid and not and the all the previous one will be marked as invalid. Which means for a particular primary key, there will be one valid record and there will be a lot of stale records. And these stale records remains on the disk until the retention cleans it up, which means since the Pinot segments are immutable, we cannot update it, which means all of these stale record will stay on the disk as long as the retention kicks in and it deletes the entire segment. So, which means it takes a lot of unnecessary disk space, and it also impacts our query performance. It impacts our cluster health and reliability that we'll see in the next slide. So that's overall why the compaction is needed. Now let's talk a little bit about evaluation of upsert tables. So all our large upsert table, it used to take a lot of disk space because there will be a lot of updates for the same primary key, and we cannot get away with it. So we started with enabling upsert compaction for these tables. So what upsert compaction does is it picks up a already committed segment and it removes all the stale record and re-uploads a compacted segment back to the table. This this improves the disk utilization, because now instead of maintaining those old record for a very long time, you are continuously updating your segment to only have the latest record and delete everything else. So this helps us with the disk wastage. But enabling this upsert compaction, we were able to reduce the disk space, but we still had another major problem, that was too many segments for a high retention table. So in this case, we were able to, since the upsert compaction only operates on a single segment, even though we were able to compact these segments, we were still re-uploading it as another segment, which means our primary keys are now scattered across multiple segments. And when you have a very large table with a high retention, it means we end up with a lot of small segments, and these smaller segments cannot be deleted as long as it is maintaining at least a one primary key. So until that one primary key is also deleted, we cannot delete the entire segment. So what we saw was, like, for some of our table, we ended up with up to 120K segments for a single table. And this means high latency. This also means that the overall ZK node, which we are using to maintain the segment metadata for a table, that is also too large, and it also impacts the ZK latency. And in some of the cases, we also saw that due to ZK query taking too long, it might impact our ingestion, it might stop ingestion. And the only solution at that time we had was to cut the retention, which means we will reduce the retention from, say, 90 days to maybe for 70 days. And that was the only way to reduce the number of segments for a particular table. So uh, to get around this issue, we came up with a custom solution within Uber where we will read the older data and we'll restream it. So what restreaming does, it puts your older data from old segment to a to a recent segment. So all the data in your older segment is now eligible for retention. As in, because all the data is now stale, you can just, during the compaction, it will see that, okay, there is no valid record. It need not upload a new segment. It need not upload a compacted segment back to the table. So this way, we were able to solve for some of the use cases by having this additional workflow that keep on re-ingesting. But this means additional workload on the user side to maintain this workload, because now you need to query the table and re-ingest the data. This also introduce additional ingestion workload or ingestion throughput for the existing topic, which is already under a lot of strain, because it's at the end, it's a large table and it has a very high retention rate. Sorry, it has a very high ingestion rate. So we are introducing additional ingestion rate just to maintain the cluster health. So these were the challenges that we have faced. And to address these challenges, we have introduced segment merge compact task, which we also call it small segment merger task. So what small segment merger task does, it picks up multiple segments at the time and then creates one compacted segment which gets uploaded to the Pinot table. And then later on, these compacted segment can also again be compacted into an even larger segment. So what this helps us is that we are able to control the segment growth, because the task can work on, like, say, 10 segment or even 15 segment and creates one compacted segment, which means the number of segments reduces drastically. With this task, we also don't need a custom workflow from the user side to maintain high retention, because we know that we will have the number of like we we will have the number of segments in a table under control, which means we don't need to have this re-ingestion workflow need to continuously replay these messages. And this also means that now all our data is co-located within a single dense segment instead of spreading across multiple segments with a very less number of primary key per segment. So this also helps up with the query performance, because now you're instead of your query scattering across multiple segments, you're just querying like a certain set of segment, and the query results are much faster. So yeah, we'll dive into like more detail on how this works. Essentially, how the component coordination work for these tasks. So here there are three components that plays crucial part of executing this task. That is the server, the controller, the server, and the minion. So the controller is responsible to submit a new task. It's up when a controller reads these tasks, reads the existing segment metadata, and creates a task, and which is then sent to the minion. We'll talk about how the segment task generation and the execution works in the next slide. But essentially, it picks up a set of segment that can be compacted into a single segment, and it submits the task to the minion. Minion then picks up the task and then calls server to fetch the valid doc ID and calls deep store to download all the servers, to download all the segments. So Minion will download whatever segment that needs to be compacted, read that, and then also use the Validoc IDs which is stored on server on server disk to know what are the records that are valid and what are the one which is not valid. And once it has all the segment and the information about what are the records that are valid, it will iterate over each of the segment and read all the valid record and create a new segment out of it, which is compacted, which only has all the valid records and creates a one compacted segment, which is then uploaded back to the controller. And controller then uploads a merge segment to deep store, and controller notifies the server that should post that particular segment to go to deep store and download it. So the server will receive this request and go to the deep store and download the compacted segment. So this is one execution of the task, and we'll go more into detail on how the generation and the execution works. So the task generation, Pinot is handled by Pinot controllers. So Pinot controller will scan all the segment metadata and identify a group of segments that can be merged. And here we follow time-based continuous strategy, which means we will keep on selecting segments to merge until we hit a, a config threshold, which can be either maximum number of segment per task. It can be maximum number of rows per segment, which is like, say, the total valid rows per segment is 5, 10, and 15, and we have configured it to be um, say 12. So if we select 5 and then 10, it will be 15. But if we go, like, if we are breaching the threshold, we'll not select that segment. So using these thresholds, we keep on selecting the number of, like, a set of segment until we breach the threshold, and we divide it into these groups. So in this image, you can see like S0, S1, and S2 can be one group, S3 can be one group, S4, S5, and S6 can be one group, and similarly S7. Once these segments are divided, we sort them based on the largest compaction gain, which is that if I were to pick this set of segment, what's the compaction gain? That is like for each invalid record, how many valid record we have, and we should pick the one where we are getting the maximum gain. So we sort them according to that, and say the first segment is the first set of segment is picked up. We will compact these and upload a new segment called compact S0 dash at the end of the segment tree. So this way, all these three are now replaced with a one single segment, which looks like this. And here you can see, like, when a controller generates a particular task, it passes all the configuration that's needed to actually execute a task to Minion. So it gives it the upload URL, which is where it should upload a merge segment. It also gives a download URL, which is the deep store URL link. So that Minion can go to that link and download these segments. And it also has like other information which is needed for the execution of the task. And I can wait for 1 minute if there is any question related to this.
There doesn't appear to be any questions at this time, but if folks want to drop in their questions in the chat later, we can address them at the later point.
Sure. Yeah. So this is how the task is generated on the controller side. And once the task is generated, it sends it to one of the available minion, and minion will pick up this task to merge this segment. So one instance of the minion will be selected, and it will read all of these from the deep store, download it, uh, process these segment each one by one. We're using the valid doc ID and only keep the one which are valid and create one compacted segment. And that compacted segment is then uploaded to controller, and controller uploads to deep store, and then server downloads it from the deep store. During this time, we saw that how a minion is compacting the segment and uploading it. And here the upload follows the same path as any regular Upsert workflow, where we call the add or replace segment to uh, add a new segment, which will process each of the primary key, and all the records in the older segments are now marked as invalid, and the Upsert metadata starts pointing to the new compacted segment. So this way, all the records in these all the records in this old segment will be marked as invalid. So essentially, these segments don't have any valid records. So we also need to take care of deletion of this. So that's done in the subsequent task execution or the task generation logic, where during the task generation, Pinot controller will also read these segments and see if there is any segment which don't have any valid records. In this case, when task one was executed, a compacted segment was uploaded, but these three still remains on disk and it still remains in the table. But then when the next execution has happened, and in between, if the snapshot of the valid doc IDs has been taken already, in that case, the valid doc IDs on the disk will be updated to say that all the records in this particular segment are now invalid. So when a controller encounters a segment where all the records are now invalid, it picks up that segment and marks it for deletion, and it uses a deletion flow to delete that segment, which means in a subsequent run, the already compacted segments are now deleted. And our table state look like this, where we have S3, S5, S7, and then a compacted segment. And eventually in the next run, it may also pick up this group to compact it and may have only just three segments like that. So we keep on picking up these segments and compacting it and re-uploading it. So that's what the merge compact task does. And we have seen some great improvement or great impact for our production table using this task. The biggest thing that we were able to do was reduce the segment count from up to 70K. This was without replication, which means overall we had 140K segments. So we were able to reduce it from 70K to less than 50K, or in this case, it's less than 10K. And similarly, we saw improvements in the query performance. We saw that the P99 was improved by up to 40 to 60% for our production use case. And we also were able to increase the retention for these tables. So eventually, since the overall um, traffic to the table or the overall ingestion rate was continuously increasing, we were continuously reducing the retention to keep supporting the use case, so that we are at least able to query the newer data, even if it means like we are not able to store or say support a larger retention. So after enabling this task, we were able to get rid of that restriction, and we were able to support whatever retention that the user wanted. And with this, we were also able to get rid of the ingestion workflow, which re-ingests the data back to the Pinot table. So yeah, overall, this has unlocked a lot of functionality for us. We are no more bounded from the limited retention of Upsert table at Uber. And this has also improved a lot on the query performance and the server reliability or the cluster reliability.
That's great, Tarun. Happy to hear that Compaction is working, and this improvement is available for the community. We did have a question come in from Anurag. The question was around when you said the controller selects the group. Does this mean it goes over all the permutations of segments, e.g. S0, S1?
So it doesn't go over all the combinations. We always select segments by time boundary, as in the time continuation. So if you're able to select S0, we check if you're able to select S1 or not. And then we check if you're able to select S2. Now, say if we include S3, one of the config here, that is one of the threshold that we have set is breaking. In that case, we will not select S3 and we'll close the group at S2 and we'll start a new group starting at S3, which means we are doing one single scan to create these groups. And all the segments that get selected are always in sequence. Like there is no, we cannot have a set of segment where we are selecting S0 and S1, S2. And then since if you're not able to select S3, we select S4. That is not possible.
Got it. So say S0 through S2 gets selected and compacted into a new segment that gets uploaded and replaces S0, S1, S2. So those are gone, and the compacted segment is then left. And then on future iterations of compaction, um, maybe the compacted segment gets selected and grouped together with S3, or um, compaction continues on forward from S3 to future segments, correct?
Yeah. It could be that it might select S3 or it might see that compacting S7 and S7 and this compacted segment, if it sees that there is more gain in compacting that, in that case, it may select that one as well. So even in this case, you can see that one of the segment that got selected was already a compacted segment. So it doesn't have to be that you can only compact a segment once. You can continue compacting it as long as the segment is available and there are invalid records.
You said that S7 could be, in theory, compacted with S0 prime, and it's
Yeah.
based off of like segment creation date or
Yeah. So
logically.
correct, correct. Logical creation rate. Yeah. Yeah. Anything else?
That's it for now. Thank you.
Okay. Cool. So next thing we can look at the commit time compaction. So here we are looking at a different challenge, but that is the inefficiency at the commit time. So we have two tasks already in Upsert where we can do compaction on segments. That is Upsert compaction task that Robert contributed, and we have merge compact task that we recently just looked at. So both of these tasks executes on minion and are sort of post data care operations, where once the segments are committed, it's on the disk. You can do these post processing and keep on reducing overall table size and keep on improving the query performance and all. But uh, one major challenge that we saw was during the commit time. Because think of a scenario where you have a table for Uber Eats, where you are storing all the state transition for a table for a particular order in Uber, which means here all the transition for that particular or a single order ID will happen within max to max 1 hour because your order is start and end is within 1 hour or so, right? So in this case, all of the updates that are happening to a particular primary key is within the same segment range because on average we commit a segment at around 4 hours or 6 hours, right? So all the updates that are happening to a particular primary key are closely followed by each other and are within the same segment. So when we commit the segment, so far we commit all the records, which means if we take this example, say we have R1, R2, R3, R4, up to R6 for three primary keys. In the older flow, we will always commit all six record on the disk and then wait for compaction or the merge compaction to kick in and pick up this segment and re-upload it as a compacted segment. But what if we can remove these stale records, which are anyway not queried, during the compaction time itself? So that's exactly what the commit time compaction does. It during the commit time, it goes through all the valid of IDs and it reads what are the one which are valid, what are the one which are not valid, and removes everything which is now stale, which is not valid. And this improves the commit time significantly because now instead of indexing each row where later we know that this is going to be invalid, we only index the rows which are valid. So this improves the commit time. This also means that you get the compaction benefit out of the box. You don't need to rely on Minion to pick up these segments and upload it, which means we are getting rid of the extra computation or extra resources required to process this. And with this, we are also able to get faster commit, because creating a segment with all of these invalid record, it needs to do a lot of processing, and then it needs to do a lot of IO to actually write the segment. But now the segment size is much smaller, which means it improves the commit time for us as well. And yeah, like some of the use cases that we saw, we were able to reduce the segment size by up to 60 to 80% after enabling the commit time compaction without any upset compaction or merge compaction job. So the technical design like this can be enabled by with single flag in upset config, where you can set enable commit time compaction to true. And once this is set, whenever we are sealing a segment, just before that, we iterate over all the valid doc IDs and exclude the one which are invalid. And during this time, we also recalculate or rebuild the dictionaries, because the segment has changed. Like it could be that you have 5 records A, B, C, D, E, A, B, C, D up to E, and then of which only B, C, and E are valid. In that case, you need to rebuild the dictionary as well, because there is no point keeping A and D in the dictionary. So in a regular flow, we use the dictionary that we had created during the mutable segment build time. But when the commit time compaction is enabled, we use the dictionary but remove all the records, all the dictionary values that are not in any of the valid records. So the dictionary size is also small. This means that we are not just reducing the size of the actual data that we are storing, but we are also improving the size of the dictionary. And uh, so if we talk about the impact, this is one of the table that we saw, where this is a test table that I had created. Uh, the one table, so one table had commit time compaction enabled, and the one did not have any commit time compaction enabled. As you can see, the segment commit time, the segment creation time is significantly lower for the table where the commit time compaction was enabled. And in this metric, you can see like how many rows we are committing for each table. So the one where the commit time compaction was not enabled, we were committing around 247 million rows. But the one where it is enabled, we were committing only 14 million rows. So this means around 90% reduction in row count. This results in around 60% reduction in table count and around 75% reduction in the segment commit time. So this ranges, like these improvements ranges between like, the kind of use case you have. If your updates are very co-located within a very short time period, then this can get like a lot of like up to 8, 10x, 5x to 10x improvement. But if the updates are spread across multiple segments, it's a on a larger time window, then it might not be that beneficial. In that case, we may still need to rely on the upset compaction. And this feature can work with the upset compaction or merge compaction as well. So theoretically, you can have a table where for the recent data, you are compacting your data using commit time compaction, and for your older data, you're using these minion tasks to do the compaction for you.
And sorry, Tarun, if I'm interrupting, but can you elaborate a little bit more on that last point you made about being able to use commit time compaction and like minion-based um, compaction together
Sure.
on the same Upsert table?
Yeah.
Like,
Uh, so there is no restriction on enabling it, because the commit time compaction only works on the consuming segment, which means it during the during the committing segment phase, we are removing all the invalid record and committing it, which means this is operating on your very recent data and only on the consuming segment. And the compaction job that we have for Minion, those operates only on the already committed segment, which is all the online segment, or I think it's called, yeah, online segment basically. So those are already committed immutable segments on which we are operating. So these are both, mutually exclusive, and we can have compaction running, which is compacting your recent data. And then say for some of the primary keys, there are few updates coming in, which is in a different segment. In that case, you might still need to use upsert compaction because now your updates are spread across multiple segments.
That makes sense. Yeah. That last point you made about, updates to a particular primary key could come after the segment is completed. So you
Yeah.
still will need compaction, minion-based compaction,
Yeah.
to remove those older records that were in the online segment that was being committed.
Yeah.
Please proceed if you have more on this topic.
No, I think that's it. If there's any question, I can take that.
Yeah, I had one more question, and I also waiting for um, the audience if they have any other remaining questions. You mentioned that commit time compaction also helps to reduce the commit time of a segment. Is that correct?
Yeah.
Mainly because there's less the older invalid records are removed,
Yeah.
and it helps to reduce the time to create indexes. Um,
Exactly. So there's lesser records to index, and also the generated segment size is much lower compared to a normal segment. So if you are removing say 80% of your rows, it means the segment size will be 60% or so. So the time taken for us to write the segment on the disk is also reduced.
Great. In the last month's session of the contributor
Mhm.
call, we discussed a feature called pauseless ingestion.
Yeah.
Have any done any work or experimentation combining commit time compaction with pauseless ingestion?
Yes, I did experiment on one table, and the feature works for that as well, because the pauseless consumption is basically creating a new segment when an existing segment is still being built. So we have not made any change on the segment base being built where I have made the change. So it can work with the pauseless consumption as well.
Perfect.
Yeah. Since the feature is already like both the features are now live and I have added the documentation as well. I'll add a note in the documentation as well that this can work with pauseless consumption as well.
Yes, and if you could share the links that you have in your slides,
Mhm.
um, I can in the chat, or you can also share them in the dedicated Slack channel. Um, I'll share that Slack channel name in a moment in the chat, but
Sure, yeah, I can do that. I just shared in the chat, but I'll do it in the Slack channel as well.
thank you, Tarun, again for presenting. Um,
Thank you. I'll stop sharing.
we'll begin our second talk now with Jiapeng. Um,
Yeah,
Take it away, Jiapeng.
my
Yes, we can see your screen.
cool. Hello everyone. This is Jiapeng from LinkedIn. Today I'm going to talk about Pinot lambda-less mode support at LinkedIn, which is also called real-time only ingestion. So, why do we need the new real-time only ingestion mode? That is because the existing mode requires table owner to maintain two separate pipelines, while the new one only needs maintaining the real-time pipeline. So before real-time only ingestion mode was introduced, Pinot table that requires real-time data with long retention period have to use hybrid ingestion mode. Hybrid table uses a lambda architecture. That means there are two separate pipelines, one nearline and one offline. which both fit to the Pinot table. The nearline one has a few days of data, while the offline one has the rest of data. In the lambda architecture, when query hit the Pinot table, they are executed on both real-time and offline data, and the results are aggregated and returned to the client. The source of the data for offline and real-time pipeline is usually the same. For LinkedIn case, there's a Kafka topic, and the data from that topic is ETL to HDFS as a source for the offline pipeline. That means the nearline transformation and the offline transformation, which the customer owned, are essentially the same. And consequently, the data that is pushed into the Pinot table is the same in both offline and nearline pipeline. The PB&J in this diagram, it's basically a Pinot build and push job, which create Pinot segments and upload the segments to Pinot. So now the question is, why don't we just have one real-time pipeline? That's because there are some challenges and missing pieces with only one real-time pipeline. The first one is data bootstrap and backfill. Unlike offline data that are batched usually every day and then pushed to the table, the real-time data is ingested in stream fashion. For real-time tables, data replacement is not as straightforward as offline pipeline, in which the segments for a day can be simply swapped with a new group of segments. Another missing piece is PI purge. PI purge was only supported for offline data as the real-time tables were short-lived, and there was no need to support it for real-time tables. The last challenge we had is small segments for having that's because having small segments normally the real-time segments are smaller than offline segments. Having smaller segments may lead to degraded query execution performance. For hybrid tables, since the retention of the real-time data is only a few days, small segment size doesn't have big effects on query performance. But for real-time only tables, there's no limit on the retention, and the data can be kept for months or years. Then having small segments with high retention is potentially problematic. We addressed all these challenges and missing pieces. For data bootstrap and backfill, we came up with an approach of time-based backfill, which we will discuss more about it in the following slides. We added the support for PI purge on real-time only tables, and we addressed the issue of small segment size by using post-processing data merge and rollup to get to the optimal segment size. Typically, a real-time only table is set up in a way that it has separate consuming and completed tenants to ensure scalability. Consuming server consumes the stream data, and after the consuming segments are committed, the controller segment relocator, which runs periodically, moves the committed segments to the completed tenant. The completed servers host the majority of the segments, and if needed, segment merge and rollup tasks compact the completed segments for efficiency. Now let's talk about data bootstrap and backfill. It is challenging due to the data layout of real-time tables, as we mentioned. The start and end time of real-time segments usually don't align with the clean time boundary. For example, if you want to do a data backfill starting from November 1st, 12 a.m. to November 2nd, 12 a.m., we cannot easily replace existing segments with new data. To handle this, we do the following in our offline job. In our case, it's a Spark job. So first, we handle the time alignment, which downloads the overlapping segments with the backfill window. For this case, it's S0 and S2. And then it converts the segments to time aligned segments by filtering out the data within the backfill window. So S0 is converted to time-aligned S0, and S2 is converted to time-aligned S2. This is handled with segment processor framework in OSS. And secondly, the job generate backfill segments as Euro. In this case, it's B0, backfill 0, and B1. Once those new segments are created, the job leverages the segment replacement protocol to automatically replace the old segments with the new segments. In this case, the old segments include the overlapping segments S0, S2, and the fully contained segments within the backfill window, which is S1. The new segments is basically all the segments, time alignments, aligned segments, and backfill segment generated in the push job. And once the atomic swap was done, we will see the segment layout in this picture. Note that this approach allows the customer to backfill data with much finer granularity compared to the hybrid solution. If the time granularity of the table is in milliseconds, the customer can basically backfill starting from any milliseconds to any milliseconds. So compared to the hybrid solution, it usually operates at a daily granularity. If the backfill window is close to current time, so in this picture, S3 is a consuming segment. And let's say the backfill window overlap with the time range of S3, we will issue a false commit before executing the step in the push job we mentioned. So the feature has been GA'd, and the new ingestion mode has reduced setup issues and operational overhead by around 50%, since only one of the two pipelines need to be maintained. One of our customers who have multiple Pinot tables reported that the offline pipeline had 27 issues in a quarter. Going real-time only for them is a huge win in terms of reducing operational toil. Real-time only also reduce the onboarding time by 30% in average based on customer feedbacks. And currently, there are 26 use cases in production. 17 of them are new use cases onboarded after the feature was GA'd. 9 use cases were migrated from hybrid to real-time only, which also includes some high QPS and high ingestion rate use cases, like who viewed my profile. For WVMP, one interesting finding there was that after it's migrated to real-time only, the query performance was increased by around 40%. And that was due to a misconfiguration configuration on the offline pipeline. It's good to highlight that moving to real-time only doesn't inherently enhance query performance, but by removing the offline process entirely, we effectively eliminate the potential for such errors. So then we have planned to migrate more use cases from hybrid to real-time only in the future. That's it. Any questions?
Hi, Jiapeng. Yeah, a couple of questions. Thanks again for this talk. I have a question around the backfill.
Yes.
Is it compatible with Upsert enabled tables?
So at Leakin, we haven't we don't have Upsert support yet. So that is not considered today. But it's on our roadmap to explore Upsert. And yeah, we will see if we I mean it's too good to have it compatible with Upsert.
Yeah, if I remember correctly, there is maybe Tarun has a better recollection around some of the backfill capabilities that they use that I think are Flink based for Upsert tables.
Yeah, we have Rohit who worked on it.
Yeah, actually, this should be supportable in backfill, but I'll just still have some caution over here with testing and do it. The idea here is if you re-upload the exact same data, the segment loading would take care of pointing to the latest record, and the tiebreaker logic that we have in Upsert metadata manager should be able to handle it. But we should still like thoroughly test and then call it out if it should work in backfill. If I understood the backfill design here correctly. Like if you're not modifying any of the time column or the comparison column values, it should work, I think.
Yeah, I think you are referring to replacing the segments with the same name. So in this case, we are actually creating a new segments with a different name and then leverage the replacement protocol to swap the segments in groups.
Will you be maintaining the partitioning logic of the uploaded segment? Because that will be the crucial point. So if your primary keys still go to the same servers that are hosting the segments, the older segments,
Yeah.
the deduplication logic would work. But in case the uploaded segments are not partitioned according to your stream, then we will start having duplicate issues.
Yeah, so partition is honored in this case. So as long as the table partition scheme align with the stream, it should be good.
Yeah.
Yeah.
And even for merge compaction, we don't replace a segment because there are multiple segments. We always re-upload it as a new segment with a different name. Yeah.
But yeah, I think it'll be good to see some validation and also call it out in a documentation if it is supportable. This is like very, very useful feature, how I see at Uber as well.
Okay, thanks again, everyone, for the conversation, for joining this session. And previous sessions are recorded and uploaded to the Apache Pinot YouTube channel. Thanks again. See you all in the future.
Thank you.
Thank you.